Hello friends, today we are going to talk about the analysis of orthogonal machining. You must have heard of metal cutting operation, you must have read about it, but in metal cutting there is a very important topic called analysis of orthogonal machining, which is important, not only important from the gate point of view, but it is the heart of this chapter of metal cutting operation. Okay, that is the only part from where you can expect a lot of questions. Almost like 80% of the questions you can expect to be asked from this particular topic if they are being asked from metal cutting operation, right? So from metal cutting operation, we are going to only talk about the analysis of orthogonal machining, right? Now, firstly, the question arises that, sir, you are talking about the analysis of orthogonal machining, but what is orthogonal machining first of all? Explain that at least first, and then we can do the analysis. Fair enough. Your query is fair. Now, what is orthogonal machining? Is that it is if the classification of the metal cutting process, if the metal cutting process is classified, you will see that it can be classified under two headings. Okay, if you see to how it can be classified, it can be classified as classification of casting process. Oh, sorry, it's not casting, it's metal cutting. Edit it, please. Classification of metal cutting process. Operation. Now, classification of metal cutting operation. How many are there? There are only two. What are they? One is 2D, two-dimensional cutting, and second is three-dimensional cutting. Fine. But sir, you were talking about the classification is, one of the classification is orthogonal cutting operation. Then where it went? Yeah. My friend, 2D, two-dimensional cutting operation is nothing but the orthogonal cutting operation. It is also known as orthogonal cutting operation. Orthogonal cutting operation. And whereas 3D operation is known as oblique cutting operation. You must have heard of oblique and orthogonal cutting operation, right? Now, what is the difference between orthogonal and oblique? Let me tell you. For that, I want you to have a look at this diagram that I'm going to make. Okay. Alright, I want you to have a look at these two figures. Have a look here. Now, could you tell me which one is orthogonal and which one is oblique? Yes, you are absolutely correct. The diagram on the left hand side, this is your orthogonal cutting operation and this is your oblique cutting operation. Now, what is the difference between these two is that there is something called feed. Do you understand what is feed? Feed is nothing but let's say the length of, let me explain you first the feed and the depth of cut, and then you will be able to understand the rest of the things very properly. let us call this length as L, and this has to be a, a turning operation. You have to turn the cylindrical workpiece from diameter D0 to diameter D1, right? And for which you are going to use one tool, single point cutting tool here. And suppose it is revolving like this, okay? So that means this part is going to come like this, and again like this, okay? It is turning like this. Now what will happen is that this length has to be turned from here till here. That means the tool has to move from here till here, isn't it? Now how this tool is going to move, what is the rate at which this tool is going to move from one point to the, from here till here, that motion is known as feed motion. Getting the point? That motion is known as feed motion. So this is your feed, okay? And it is given by mm per revolution. So there is a certain amount of distance this tool is going to travel after every revolution of the workpiece. I hope you're getting my point. After every revolution of this workpiece, this tool is going to move in this direction. Getting the point? Very good. So that is given as mm per revolution. Similarly, this tool is given certain movement over here also, but it is fixed. It is known as depth of cut. Okay, it is known as depth of cut, and its unit is in mm. So for one particular pass, depth of cut is kept constant. Okay, and suppose the diameter is, let's say, 50 mm, and after turning you require 46 mm of the diameter. That means the depth of cut could be, let us call it 2 mm. Then the depth of cut is 2 mm, and it is going to be constant throughout. So 2 mm reduction over here and 2 mm reduction over here. That means in totality you are reducing the diameter by 4 mm. That means you are going to get 46 mm, like that. I hope that you have understood. Similarly, over here you will find the same thing. This is the feed and this is your depth of cut. This is depth of cut and this is feed. Now the only difference is that in orthogonal turning operation, can you see the cutting edge? Can you tell me the cutting edge over here? Yes, you are absolutely correct. This edge that you can see over here, I am marking in red. Okay, this edge is your cutting edge. Okay, so this is your cutting edge, and can you see what is the relation? What is the angle between cutting edge and the feed? Yes, absolutely. It is 90 degrees. So this is feed and this is your cutting edge. They are 90 degree to each other, isn't it? They are normal to each other, and in such cases. So such cases are known as orthogonal cutting operation. Similarly, in oblique cutting operation, it is exactly opposite of it. You can see the cutting edge is not at all perpendicular to the feed motion. Feed motion is over here, whereas it makes a certain angle with the cutting edge. And because of which the thrust force gets divided into different components. I'm going to tell you about that also. As of now, you can see this feed is not perpendicular to the cutting edge, and that is why it is known as oblique cutting operation. And why orthogonal cutting operation is known as two-dimensional cutting operation? For that also we have a reason that there are two types of forces that we are going to discuss about. As of now, if I tell you now, you might get a little confused. So that is why I'm afraid to tell you right now. And but anyways, listen up. That there are two main forces, and what are they? One is cutting force and one is thrust force. Okay. To explain this concept, I take this example, this analogy of carpenter. You must have seen that some furniture work that goes on in your home, for which the carpenter brings along some few tools, right? And those tools, you must have seen that there is a tool which looks like a duster. It's a small, cuboid, or it's like a small piece of wood, and it has one blade, metal blade stuck into it, and it is used to shave the wood. I hope you are getting my point, which tool I'm talking about. I don't know the name of that carpenter's tool, but so yeah, that tool, yeah, I'm going to ask you to consider that tool. Okay, now suppose you want to finish the wooden workpiece using that tool. Don't you think there are more than two forces you are going to apply? No? Okay, let me tell you more about it. imagine you are holding that tool. Let us see, this duster is that tool, and there is a blade over here, okay? And now you are going to move it over the wooden workpiece. And because of which, what will happen? The wood shavings will come out like this, isn't it? Yeah, very good. And yes, so you are actually forcing this tool to move in this direction. At the same time, you are also pressing it against the wooden workpiece. No? I hope that you are able to follow. Try to follow it even more. You are moving it over here. That means you are applying the force in this direction. At the same time, you are pressing it down into the workpiece so that you can obtain thicker wood shavings. Isn't it? More and more wood could be simply shaved off. Isn't it? Yeah. So that means there are two forces that we are applying in the carpenter's tool. The same concept you can, the same concept you will find over here, that there are two forces. Which one? The first one is your cutting force. So this forward movement of that carpenter's tool is known as cutting force, and the force that sticks your cutting tool with the workpiece is known as thrust force. Okay, so basically there are two forces, cutting force and the thrust force. I hope that you are getting the point. I simply tried to relate it with your carpenter's tool, right? Very good. So the same thing happens over here. I'm not going to tell you about the directions of the cutting force and the thrust force as of now, otherwise you will get confused. So that is why just simply you can understand that in case of orthogonal machining, there are only two forces. One is cutting force and the thrust force. Whereas in oblique machining, you will find that the thrust force gets divided into two components. One is thrust force radial and the other one is thrust force axial, along with a cutting force. So you can see in oblique cutting operation, there are in totality there are three cutting forces. Okay, I mean the three forces: cutting force, thrust force axial, and thrust force radial. That's all. Whereas in orthogonal turning operation, there are only two forces: cutting force and the thrust force. Got the point? Right now, I am not telling you about the directions, otherwise you will get confused. Yeah. Very good. So now that you have understood the orthogonal machining, the concept of orthogonal machining, now let us try to analyze the forces and different parameters attached to that. Okay. Now analysis of orthogonal machining we are going to begin. But before beginning it, there are certain set of assumptions that we have to consider. Just like other theories also, in mechanical engineering, many theories are based upon assumptions. Isn't it? Before starting, we are asked to consider certain assumptions. Alright? Yeah. So those assumptions are, you can see it over the screen. You can see that the first assumption you can see is that the tool is perfectly sharp and there is no contact along the clearance phase. Fine, fair enough. We say the tool is perfectly sharp and there is no contact along the clearance phase. Fine, which is correct, which has to be there, isn't it? Second assumption, the cutting edge of the tool remains normal to the direction of the tool feed or the work feed. My friends, listen up carefully, try to note it down carefully, because this second assumption is actually the parameter which defines the orthogonal machining operation. Isn't it? This is the parameter that separates orthogonal machining operation with rest of the other machining operations. The cutting edge of the tool remains perpendicular to the direction of the work feed or the tool feed. Very good. Now the third assumption is direction of the chip flow velocity is normal to the cutting edge of the tool. Direction of the chip flow velocity is normal to the cutting edge of the tool. Very soon you are going to learn about the velocity of the chip and the direction of the chip flow, right? And you will find that in orthogonal machining, the direction of the chip flow is directed just, along the rake phase, okay? And Okay, I will be telling you more about that in detail later on. Otherwise, there is no point in explaining it now. You will not be able to follow up to that level. Next assumption is the cutting edge is a straight line extending perpendicular to the direction of motion and generates a plane surface as the work moves past it. So this is your fourth assumption. You can see it on your screens, right? Let us move to the next assumption, that the chip does not flow to either side. That means the chip only flows along the rake face of the tool and it does not flow on the either side, maybe right or left. No, nothing like that, only upward direction. The depth of cut is constant, fine. Width of the tool is greater than that of the workpiece. It's a very nice assumption. You must have seen that in oblique cutting operation or even in orthogonal turning operation, what I did was that I made the cutting edge of the tool greater than the width of cut. Did you observe that? You can observe if you have made the same diagrams on your notebook, you can see that the cutting edge I have made is greater than the width of cut. Okay. Now the next assumption is the work moves relative to the tool with uniform velocity. And next, as a continuous chip is produced with no built-up edge. I hope that you are aware of built-up edge, right? If not, then let me tell you that built-up edge is nothing but it's an edge that has been built up. Right? Did not follow? Okay. Yeah, of course, because I did not say anything new about it. So its built-up edge is nothing but it's an edge that has been built up, which was not there earlier. And where it has been created? At the tip of the tool. Okay. So if you observe, suppose this is your cutting tool, and this is your work material. So this is your tool, and this is your chip formation taking place. It's a rough diagram I'm making, alright? I'm drawing a rough diagram, so yes, like this, okay? So you will see this is your T1, which is known as uncut chip thickness, and this is known as T2, which is known as cut chip thickness, simply chip thickness. So you will find that at this tip of the tool, where is the tip of the tool? Here it is, right? So here at the tip of the tool, small particles of this material, this work material, will start to get welded at the tip of the tool. They will get welded over here. And because of one obstruction, it will lead to several other obstructions, and more and more small particles will start to stick at the tip of the tool, okay, because of obstructions. And so you will find that as the machining process continues, this part grows bigger and bigger and bigger. So this part will become bigger and bigger and bigger. And at one point of time, what will happen? This globule, okay, will become so big or so huge that it won't be able to handle the pressure because of the work material. So it is going to collapse. And when it will collapse, some part of it is going to get carried by the surface or finished surface of the workpiece. This part is a new surface, a machined surface, right? So ideally it should be very smooth and very shiny, right? But because of the collapse of your built-up edge, a small particle will stick over here, will get welded over here, okay? And as a result, it is going to damage the surface finish, okay? It is going to hamper the surface finish. And some part of it will also be carried away by the chips, like this. Yeah, so, and this kind of chip is known as the chips with built-up edge. Yeah, very good. So this is what I wanted to tell you. And so these are the assumptions, my friends, that we have to consider. And now let us directly jump to the analysis, okay? Okay, now in the analysis, what you have to do is, firstly, you need to make one diagram. Now, what diagram, sir? This diagram. Firstly, I will make the planes like this. Then I'm going to show the tool like this. And I hope that you are aware of the angles of the tool, right? Okay. I hope that you are well aware of the tool geometry. Considering that basic information, I am going to explain you about the orthogonal machining operation. Okay. So you will find here that this angle that tool rake face makes with the vertical is alpha, isn't it? It is nothing but the back rake angle. If I hope that you remember, it's a back rake angle. Okay, it's back rake angle, and we are actually considering a small part of the tool. Okay, actually this tool extends till over here. Let me give you the just an idea. Like it extends like this. It extends like this. So I hope that you can picturize it, right? So it's a small part of the tool which we are considering. Okay, so don't worry about that. Like this. So this is your alpha, and this angle is your clearance angle. Okay, clearance angle means a relief angle that is provided so that the tool should not rub against the finished surface of the workpiece. Okay. Suppose it is like this, then what is going to happen? The entire length of the tool is going to rub against the surface finish of the workpiece. But we don't want it, so that's fine. And you have seen that this angle here, you must be knowing that this is your shear angle. Okay. Now, what is a shear angle? Shear angle is the angle of the shear plane with respect to the horizontal. Okay. So now, sir, where is the shear plane? My friend, shear plane is this plane that you have drawn here. Yeah. So this inclined plane is nothing but the shear plane, right? Very good. Now, sir, shear plane, is it really a plane, or it is an ideal assumption, something like that? A very good question, I would say. This plane is not a plane actually. There are two shear zones. First of all, let us understand about the shear zones. So there are in totality two shear zones, primary and secondary. Now, where is primary shear zone lie? Primary shear zone would lie over here at this part. Let me draw it. Let me explain it to you properly. So the primary shear zone is going to lie over here like this. Okay, this is your primary shear zone. Similarly, secondary shear zone will lie somewhere over here like this. Okay. Now, primary shear zone is a zone from where the chip formation starts or formation takes place. Chip formation takes place, right? So, chip are being formed. That means that chip must be getting separated from the workpiece at some or the other point, isn't it? Yes. So, what is that point where it is getting separated from? It is this region actually. It's not a point. It's a region in which all these things happen. But since this is difficult to follow, what we assume is that this is not a region, it is just a plane, so that the things become easier for us. Okay, so that is what we do. So the primary shear zone is considered to be simply a shear plane like this, and we don't consider the rest of the volume or the area of the zone. Yeah. I hope that you have understood. Now coming to the secondary shear zone. Secondary shear zone occurs because of constant sliding action of the chips at the surface of at the rake surface of the tool. You can see this is the rake surface of the tool. I hope that you know it about it, right? And this chip is constantly flowing over the rake face of the tool, and it is rubbing. Constantly it is rubbing. And now because of which, what will happen? There is a wear called crater wear, and crater wear is, we will talk about that later, or you can study on your own. And it happens because of the same thing. This isn't it, because of the chip and rake face interaction. There are certain other things also which leads to the crater wear that we are not including as of now, right? And so this is nothing but the secondary shear zone, what we can understand. But since we don't have anything to do with the secondary shear zone in analysis of orthogonal machining, so we are not going to consider it at all. Okay, we are not going to even talk about it. So let me simply rub it off. Right. So we have got alpha, we have got phi, and we have got clearance angle. Let us call it theta. Although we don't actually require this also. Right. Now, what is the movement of the cutting tool? Could you tell me? This tool is moving, it must be moving in this direction, and that is why this chip is moving in this direction. Again, try to relate it with your carpenter's tool, isn't it? You used to move it like this, the chip used to flow like this. Similarly, we are moving like this, and the chips are flowing like this. Got the point? Very good. So that means this is the direction of the cutting force. This is the direction of the cutting force, and as I told you, you have to press the carpenter's tool against the wooden workpiece so that you can dig more and more of the wood, right? So which is nothing but the FT. So in a similar manner, we are also pressing it against the workpiece like this. Now if the cutting force is in this direction, my friend, don't you think that cutting velocity is also in this direction? Yes, absolutely. The cutting velocity is also in this direction. Now, there is something called chip flow velocity. So the chip flow velocity goes like this. You can see that the chips are moving along the rake face of the tool. When you study about the geometries of the tool, there you will see that the rake angle, the back rake angle of the tool guides the chip flow. It is the angle which is responsible for the movement of the chip after chips are formed. So where the chip is going to flow is decided by the rake angle, right, or the rake face. So you can see this is the rake face. So the velocity of the chip flow is also going to be parallel along to that. Now you may ask, sir, but you have represented it's like curling, Now my friend, the curling happens because of some other reason. Right, because the chip that comes out, it is in extremely heated state. It is very hot, and when it comes out of the atmosphere it gets separated to the workpiece from the workpiece. I'm sorry. It cools down, right, and because of which, and because of the thermal characteristics of this material, it gets curled up. Because of the properties of the material, it gets curled up. But essentially, if you talk about the movement of the chip, it will happen along the rake face of the tool. I hope that you have understood. There is no need of further explanation. Now, there is one more velocity. You can see it on your screen also. That there is one shear velocity, right? So, shear velocity happens along the shear plane. Okay, shear velocity happens along the shear plane. So now what I have seen is there are three velocities in orthogonal machining operation. One is cutting velocity, which is in this direction because the tool is moving in this direction, and because of which chip formation takes place and chip flow along the rake face of the tool, because that is what we learned in our tool geometry, right? And then we have also seen the shear velocity, which happens along the shear plane of the material, of the system, right? Very good. Now, there is something that I want to tell you, that you must be wondering, sir, what is cutting velocity? Okay, we have understood what is cutting velocity. What is chip flow velocity is also what we have understood. But what is shear velocity, sir? Please explain me about that. Very good. So what is shear velocity and what is chip flow velocity? We are going to talk about these two things. Cutting velocity is simply the relative motion of the tool with the workpiece, and vice versa. Why vice versa? Because it is not always compulsory for the tool to move. Sometimes the workpiece also moves, right? As you must have seen in shaper and planer machine, right? In shaping machine, the tool reciprocates like this, isn't it? Whereas in planing machine, the work moves and the tool is stationary. The work moves and the tool is stationary. Getting the point? Very good. And why there is a difference between, why the planer machine was developed, why shaper machine was not sufficient or what? Yes, absolutely. Shaper machine has has some limitations. What are those? That in shaper machine, the tool moves along with the ram. There is a ram that moves the tool like this. Getting the point? And if suppose the workpiece is longer, you have a longer workpiece, then what will happen? This tool along with this ram has to travel for the longer distance, isn't it? And don't you think so? When it is going to move like this, it is going to slack down because of its own weight. Yeah. And when it is going to slack down because of its own weight, what will happen? You will find that you are not obtaining a horizontal surface, right? Instead, there will be a tapered surface you are going to obtain. So wherever the length of the workpiece is more than the movement of the ram or the tool in shaping machine, we go for planing machine. I hope that you have understood. Now let us come back over here. So cutting velocity you have understood. Now chip flow velocity and shear velocity we are going to talk about. So please note it down that chip flow velocity is the chip flow velocity with respect to what? The tool or the workpiece? It is with respect to the tool. Okay, with respect to the tool. Similarly, there is shear velocity, which is the chip flow. Again, it is the chip flow only. Yeah, chip flow velocity itself, but with respect to the workpiece. Now, in exams, they ask the questions in variety of ways, okay, variety of manners, and they try to confuse you with whatever way possible. If you are conceptually strong, you will not be confused. You cannot be confused. So what they try to do is they will try to confuse you with the words, okay, with the language, or with the description. So they might ask you, find out the chip flow velocity with respect to the tool, and also the chip flow velocity with respect to the workpiece. Now, if you don't know the exact definition of VF and VS, you are going to fall into this trap, right? So that is why it is important and it was worth mentioning. I hope that you have got the point. Let us proceed further. Now that is why it becomes very important to find out the relationship between all these three velocities, okay? So what I am going to do is I am going to make a vector diagram here. So you will see that VC is in this direction. So this is the direction for VC. Similarly, VF, you can see VF over here. It is like this. And similarly, VS it's in this direction. This is VS. Now, what would be the angles between all these three sides? The first thing that I can think of is phi, because phi is immediately, it is just in front of me. This is VC and this is VS. So the angle between VC and VS is nothing but phi, because VS happens along the shear plane. So this will be phi here. And what is the angle between VF and VC? Let us see. So VF actually happens along the rake face of the tool. Okay, along the rake face of the tool. That means, what is this angle here in between them? If we forget theta here, because theta, we don't want answers in terms of theta here. Okay. So you can see this angle is nothing but 90 minus alpha. I hope it is clear to you. We are concerned about this angle here, and it is 90 minus alpha, right? This is 90 minus alpha, and that's why this is going to be 180 minus 90 minus alpha plus phi, which I can say as 90 plus phi plus alpha minus phi. Okay, yes, 90 plus alpha minus phi. Yes. Now I hope that you remember the Lami's theorem. I hope we remember Lami's theorem. Yes. So Lami's theorem can be applied for this triangle. So you will see that VC divided by sine of the opposite angle of VC. So that means this. So sine of 90 plus alpha minus phi is equal to VF divided by sine of its opposite angle. So sine of phi, and similarly VS sine of its opposite angle, which is 90 minus alpha. 90 minus alpha. So VC divided by sine I'm going to write it as phi minus alpha, although you can write it as alpha minus phi also. But okay, this is not sine, this is cos, okay? Sine 90 plus something is cos plus something. So, or cos something. And now Vf by sine phi and Vs by cos alpha. So this is the relation that I have got. I hope that you are also getting the same results. Yeah. Let me confirm it. Vc cos phi minus alpha, Vf sin phi, Vs by cos alpha. It's absolutely correct, and you can note it down now. So this is the these are the relation between three velocities. Okay. So this is just one step in orthogonal machining operation. Okay. Now, after the analysis, after the relationship between the velocities, we are going to talk about the shear angle. Okay, we have to find out an expression to calculate shear angle. Okay, so we have just now seen the relationship between velocities, and now it's time to talk about the second. What do you call? I mean, there is one more thing that we need to form. There is another equation that we need to derive, okay? And for which, what we are going to do is, firstly, let me tell you, this derivation is for the shear angle. And now what is the shear angle? Shear angle is this angle that you can see over here. And as I told you, shear angle is the angle formed by the horizontal and the shear plane. Getting the point? Yeah. Now the shear plane is it a fixed quantity or it is a variable? My friends, remember one thing, that out of all the angles in analysis of orthogonal machining, out of all the angles, shear angle is the only angle that is a variable, okay, that you have to come across with. So shear angle is a variable and it varies with different parameters. It varies with the velocity. It varies with the cutting speed. It varies with the material, with the workpiece material. It varies with the with the cutting fluid that you are going to use. Okay, because shear plane is a region from where the chipping action is taking place. So it is not fixed. It is not a fixed quantity. Okay, it is going to vary, and that is why you will see that there are other things also. I mean, there are certain other techniques through which you can determine phi. But for a given system, suppose you have been given the rake angle, and you have been given the thicknesses of the chip and the uncut chip thickness, you will see how this phi or the shear angle can be derived out of these quantities. Alright, so let us start. So firstly, the first and foremost thing I'm going to do is, I'm going to mark these thicknesses over here. Let us call it T1 and let us call it T2. Now this is your T2. T2 is your chip thickness, T1 is the uncut chip thickness. Now I am going to draw certain construction over here, that I am going to drop one perpendicular from this point on this line. Okay, let me call it A, let me call it B, and this is C. And similarly, the same thing I am going to do here. So this is your point D. Okay, and it is perpendicular on the rake face of the tool. Although it doesn't look perpendicular in my diagram, but it is perpendicular. Okay. Now what we are going to do is, can you tell me what is sine phi? Sine phi is BC by AB, right? Now what is BC? BC is the perpendicular on AC. So can't I replace it with T1? Yes, of course I can do that. And that is why I can also write AB as T1 by sine phi, okay? T1 by sine phi. So this is my first equation. And in a similar manner, I'm going to consider now the other triangle ABD, and in this triangle, I'm interested to know this angle in blue. This angle. Now, could you tell me what this angle would be? Yeah, this angle is nothing but a small part of alpha is involved and the rest of this angle. which has been left after phi. So it is alpha plus 90 minus phi. Yeah, very good. I hope that you have understood. So it is, again I am going to take sine as 90 minus phi plus alpha. 90 minus phi plus alpha. Now it is also equal to BD divided by AB. Now what is BD? It is T2 divided by AB. And so we can write that cos phi minus alpha is equal to T2 by AB. Or also I can write it as AB equal to T2 by cos phi minus alpha. Now let me call it equation 2. Now you can see this, these are two AB's values. Let us equate both of them, equating 1 and 2. You will find T1 by sin phi is equal to T2 by cos phi minus alpha. Cos phi minus alpha. Now, I am going to write, rearrange it. So T1 by T2 I am going to write. Now what is T1 by T2? You must have heard of one parameter which is known as chip thickness ratio, and T1 by T2 is chip thickness ratio, and it is indicated, it is represented by R. Okay, so T1 by T2 is equal to R, and it is equal to sin phi by cos phi minus alpha. Cos phi minus alpha. Right? R equal to sin phi by cos phi minus alpha. Now I am going to expand cos phi minus alpha. I can also write it as sin phi divided by cos phi cos alpha plus sin phi and sin alpha. To simplify it further, I am going to divide the numerator and denominator by cos phi. So what I get is R is equal to tan phi divided by tan phi, divided by cos alpha only, because cos phi will get cancelled out. So cos alpha plus tan phi and then sin alpha, right? So this is my final equation that I have got, but we can simplify it even further, and we can write this equation in terms of tan phi, that tan phi equals to something. Let us see what it is. So you will, if you rearrange the same equation, you will find that tan phi is equal to R cos alpha divided by 1 minus R sin alpha. Okay, so this is, you must have seen this equation in your notebooks also, in your textbooks also. This is a very common equation, and you can see phi is your shear angle, and it depends upon alpha and R only and nothing else. Yes, so this is how you are going to calculate for shear angle, right? Now my friends, we are going to proceed to the most important topic in analysis of orthogonal machining. Okay, now what is that? That is the analysis of the forces, right? Now what are the forces? You have already told me about the cutting force and the thrust force, right? So are there any other forces apart from that? Yes, actually there are in totality 6 forces that you need to consider in analysis of orthogonal machining operation. So there are in totality 6 forces. Now what are they? We'll talk about that after a while, after some time. But before that, let us understand the cutting force and the thrust force. Out of these 6 forces, let me tell you what are those. I'm just going to name them, not going to describe them. So we will start with FC and FT. And let me tell you, these all 6 forces come in pair. Okay, that means there are 3 pairs of 2. So FC and FT, cutting force and thrust force. Similarly, there is friction force F and a normal force, normal component to the frictional force. Okay, and similarly there is one shear force, and there is one normal force to the shear force. So you can see 1, 2 and 3 pairs, totality 6 forces. And out of these 6 forces, only FC and FT are the forces that are measurable. Okay, these are the measurable forces. These are the measurable forces. And so then what about Fs, Fn, F and N? My friends, these forces actually they occur in a dynamic environment, and that is why they cannot be measured. Okay, but sir, how you are going to measure cutting force and the thrust force? My friend, there is a small technique. And what is the technique? The technique is that you have an instrument called dynamometer. Okay, and the people who are still they are studying in college, you can anytime go to lab and ask the lab in charge to show you the dynamometer. He must be having it. Okay, it is a very common gadget. Okay, so what happens there is that there is an instrument. It's a digital instrument, and it has 2 probes, and it goes into the tool. Okay, you're going to connect that with the tool in lathe machine. Suppose you're performing a turning operation, you're going to attach the tool with the dynamometer. And when you will start start machining the workpiece, you will find that there are 2 categories. One shows the value of FC and other shows the value of FT. Right? So in this manner, you can measure the forces of measure the magnitude of cutting force and the thrust force. Right? Now what happens is that the friction force, where does it occur? Friction force occurs, yes, absolutely, you are right. It happens over at the chip and rake face interface. Right? Chip and the tool's rake face interface. So whenever the chip is going to move like this, don't you think that this rake face, the friction force will try to oppose its motion? Isn't it? Yes. So that is the friction force I am talking about. And since it happens in an inclined way, yeah, it is going to happen in inclined manner. So there has to be one normal force attached to that. We will come to that point later. And then there is a shear force. What is shear force? Shear force means the force required to shear off the material. When this tool is moving in this direction, don't you think that this workpiece is going to offer certain amount of resistance for not to getting sheared away? Isn't it? So that is the force that I am talking about. Now, along which direction it is going to happen? Yes, it is going to happen along the shear plane, right? Because the material is getting sheared away from the shear plane only, right? So the shear force is going to act along that plane. Very good. And similarly, shear plane is also, because it is inclined, the shear force will also be inclined, and that is why there is a need for a perpendicular force or a force normal to the shear force. Getting the point? Yeah. So these are the 6 forces that you need to see. So what we are going to do, this friction force and the shear force, they also consume certain amount of power. Okay. And what is total power actually? Power is given by Fc into Vc. Okay. So the cutting force multiplied by the cutting velocity will give you the complete power consumption. But this total power consumption is actually, if you go into detail, you will find that this total power consumption is in fact the summation of individual power consumptions. How many? 2 individual power consumptions. What are they? These 2 power consumptions are because of these forces, these 2 set of forces. Getting the point? So certain amount of power is consumed for overcoming the friction, and certain amount of power is consumed for shearing the material away. Right? And Fc into Vc, the total power consumption is just the total summation of these 2 things. I hope it is clear. Right? Now we will proceed further now. So actually what we have to do is, because there is a power consumption, individual power consumption, because of these 4 forces also, and since these forces cannot be measured, so what we have to do is we have to try to come up with some solution. And what is the solution? Is the relationship between measurable forces and unmeasurable forces, so that unmeasurable forces can be directly found out using that expression, because there is one measurable force and we can measure the other forces very easily. Getting the point? I hope that you have got the point what we have to do, right? Now let us begin our discussion. So since we know the friction force, firstly we will do one thing. We will mark all the forces, okay? So the cutting force will be in this direction. Friction force will be in this direction. Because the chip is moving like this, friction is opposing it like this. And the shear force would be acting in which direction? It is going to act in this direction. The shear force is going to act in this direction. Got the point? Yes. Now what I'm going to do is, since I know the cut, okay, now where is the thrust force? Thrust force also we know, right? Thrust force acts perpendicularly to the FC. Going back to the carpenter's tool, the motion of the carpenter tool is in this direction, but you actually apply it, you press it down perpendicular to the cutting force, the direction of the cutting force, right? So they are perpendicular to each other. Very good. So that means if FC and FT are known, so their resultant could be found out, isn't it? So what we are trying to do is, my friend, we know two measurable forces. And they both are perpendicular to each other. That means one force is like this, another is like this. So this is FC and this is FT. Then what will be the resultant? This is going to be the resultant. Don't you think so? And what will be the magnitude of this resultant? This resultant can be written as R equal to under root of FC square plus FT square. Like this. Got the point? Yes. Now, my friends, in the analysis of the orthogonal machining, we are going to use one geometrical approach, which is known as merchant circle diagram. I hope that you are aware of merchant circle diagram. If not, then you are going to learn it over here. The merchant circle diagram is a geometrical approach. Okay, by measuring the lengths of the lines indicating individual forces, you are going to determine the magnitude of those individual forces. I hope it's clear. Okay, so what I mean to say is, suppose, let us take an example, okay? Suppose FC is, let's say it's 1000 Newton and FT is 500 Newton. So what will be the resultant? The resultant will be, let us see how much it is going to be. So it will be 1000 square plus 500 square and under root of this. So it will be 1118. Okay. So it will be 1118. Simply, I am not considering the decimals. Okay. Just to make it simpler. Now you can see this is the resultant you have already got. Now we are moving towards the merchant circle diagram, and for which what we need to do is we need to have a resultant here. I consider that 1 centimeter of length of any line I'm choosing on scale. Okay, the scale means you must have seen in the maps that this much is 200 kilometer, 200 meter, like that. Yeah. So similarly, 1 centimeter signifies let's say 100 Newton. That means FC, the length for FC will be how many Newton? How many centimeters? Yes, absolutely, 10 centimeter. Similarly, FT will be shown by 5 centimeter line. Getting the point? And what will be the length of resultant here? Because it is 1118, that means simply divide it by how much? 100. Okay, that means it will be 11.18 centimeter. Got the point? Very good. So what I am going to do is, I am going to FC is in this direction, so I am going to draw 10 centimeter line. Okay, I am going to draw 10 centimeter line where Let me draw it over here. Okay, let me draw it from the tip of the tool. I'm going to draw it like this. Suppose this is FC, which is 10 centimeter long, and I know that FT is perpendicular to FC and its length according to its magnitude is 5 centimeter. So I'm going to draw it like this, right? So this is your FT, and the resultant will automatically be 11.18 centimeters. So this is your resultant, like this. Okay, try to follow what we have done so far. I have assumed FC to be 1000, FT 500. So resultant is this much, and FC's, according to the scale, FC's length will be 10 centimeter, FT 5 centimeter, and R 1.18 centimeter. I have taken the scales and I have drawn these three lines here. I hope there is no confusion. Now in merchant circle diagram, what is the rule? What he says is that taking this resultant as the diameter, okay, taking this resultant as the diameter, draw one circle, right? Okay, so let us draw a circle. When you draw a circle, and since these are perpendicular, so, and this is the diameter, don't you think it is going to, it is come over here like this? It will become something like this. It will look something like this, okay? I don't know how far it is visible to you. Yes, it is pretty much visible, right? So this is nothing but a circle that we have made. That's all. Now what he says, if you want to find out the unmeasurable forces, simply draw them along, okay? So, okay. Now I want to ask you, what is the direction of the friction force? It is along this direction, isn't it? Along the rake face. So don't you think if you can simply extend it like this till over here, yeah, into this diagram, till here, it is your friction force. And I know there is, what is N? N is the normal force perpendicular to the friction force. So I'm going to draw a normal force like this. So this is your N, right? So what I have got is friction force and its normal. Now what I'm going to do is I'm going to take a scale, a ruler. I'm going to measure the length of this friction force, right? Suppose I got, let's say, 11 centimeters, right? That means according to the scale, its magnitude is 1100 Newton, isn't it? And suppose this N is, it looks very small, let's say it is 4 centimeter. That means it is 400 Newton. Getting the point? It's a wonderful method. Similarly, you can show the shear force over here. So the shear force goes like this, from here till here. Yeah, shear force is like this. Simply draw the one line like this, in this direction. So this is your shear force from here till here. This is Fs. And now, simply join this point to this point. It will automatically be 90 degree, first of all. This will automatically become 90 degree, and this will become your Fn. So you see, shear force is looks very small. It looks very small here, and let's say it is 6 centimeter long. That means it is 600 Newton. And what is Fn? Fn, simply measure it. It will come around 8 centimeter. If it comes around 8 centimeter, that means it is 800 Newton, like that. I am simply assuming the things, okay? For that, you need to measure it accurately. So this is a graphical approach. Getting the point? Very good. So this is nothing but the first step of analysis of the forces in orthogonal machining, right? Now, there is one diagram in front of you, which is forces in orthogonal machining. You will find exactly same figure being drawn over here, right? It looks just like this only, right? So yeah, so you now understand that how we have got that circular diagram, isn't it? Very good. Now, but gate exam, you cannot draw this entire merchant circle again and again, and for that what we need to do is we need to form few expressions or few relations, so that without even drawing it completely we can deduce the answers, right? So it's very easy actually. So let us have a look. You will find that this alpha, if this is alpha, don't you think this is going to be alpha? And for this analysis, you have to be really patient, because there are so many angles and different forces are there, and it might become complicated, it might become confusing, but if you are patient and attentive, you are going to follow it like anything. It's very easy actually. Okay, so if this is alpha, and there is one more angle you can see on your screen, which is beta, and beta is nothing but the friction angle. And from the past experience from engineering mechanics, you must be knowing what is beta. Beta is nothing but the angle between resultant and n. Okay, yes. So this is beta. Now if this is 90 degree, then what is this angle? If this is 90 and this is beta, we are going to consider three triangles. Okay, we are not going to mix them up. So firstly I'm considering the triangle with sides F and an R. Similarly, there will be another set of forces, that means another triangle, FC, FT and R. Similarly, another set of forces, another triangle, which is FS, FN and R. I hope you are getting the point. So I'm considering firstly F, N and R, and in this triangle, this is 90 degree, this is beta, that means this angle is 90 minus beta. This angle will be 90 minus beta. First, let us talk about all the angles. Similarly, let us consider the triangle FS, FN and R. Okay, FS, FN and R. So if this is alpha, this is 90 minus beta, what is this angle here first of all? What is this angle? Yeah, okay, this angle, I know, this angle is what? Can you determine what is this angle? This is the angle of the shear force along the shear plane. That means shear angle is the angle made by Fs and the horizontal. So that means this angle is phi. Very good. My things are becoming easier. So if this is phi, this is 90 minus beta, this is alpha. This is the only angle that I don't know, right? And I'm talking about the triangle Fs, Fn and R. So if one is 90 degree, what is this angle? If this is phi, I can see this is 90 degree because this is one plane along the axis. This is one axis, this is another axis, and that means 90 degree. This is alpha, 90 minus beta. That means it is 90 minus beta plus alpha. Okay, I'm going to write it over here. So the angle between angle FC and R, okay, angle FC between FC and R, okay, let me, in triangle FS, FN and R, angle FS and FN is 90 degree, and angle R and FC is 90 minus beta plus alpha. So if you can write it as, so it will become beta minus alpha. So it will become beta minus alpha. Angle RFC will become beta minus alpha. Okay. Similarly, angle FN and R, you will find, because the entire is 180 degree, right? So 180 degrees minus 90, which is this angle, plus phi plus beta minus alpha. Phi plus beta minus alpha. So you will see that angle FN and R is 90 minus phi minus beta plus alpha. Like this. Okay. So this angle is this much. I'm going to write it over here. It is 90 minus phi plus, 90 minus phi minus beta plus alpha, like this. And similarly, you can find the angles for FC and FT. You can see FC, this is 90, this is beta minus alpha. I'm talking over the triangle FC, FT and R. This angle is known, this is 90. That means this angle will be this angle between FT and R, angle FT and R. You will see it will be 180 minus of what? Beta minus alpha plus 90. So it will be 90 minus beta plus alpha. That's all. Okay. Right. So I have written down all the angles. If you are confused, just pause the video and try to figure out. It's pure geometry. You are going to follow it like anything. Okay. So there is no confusion at all. Now what I am going to do is, if I now I'm going to again consider the Lami's theorem, and I'm going to find out the relationship between the sides and the angles. Okay, right. So I'm going to firstly take the triangle F, N and R. In triangle, R is equal to R divided by sine 90. It is equal to F divided by sine beta, and N divided by sine 90 minus beta, which can be written as N by cos beta. Okay, so you can rearrange it. So R is equal to F by sine beta is equal to N by cos beta. Okay, so you have got one set of relationship. R is equal to F by sine, N by cos beta. Very good. Similarly, you can consider the other triangle, which is Fs, Fn and R. So R will be again R by sine 90. Fs divided by Fs, and its opposite angle is this much, right? So sine of 90 minus phi minus beta plus alpha is equal to Fn divided by phi plus beta minus alpha, right? So it will be sine phi plus beta minus alpha. Okay. Now again I am going to rearrange it. So I will get R equals Fn by sine phi plus beta minus alpha equals Fs divided by cos phi plus beta minus alpha. Again I have got two more equations like this, and both are equal to R. This R and this R are same, right? So that means I have got a relationship between F and Fn, and all these four forces can be related to each other, right? And also you can find that there is some kind of pattern, isn't it? F by sine beta, N by cos beta. Fn by sine something is equal to Fs by cos the exact something, isn't it? Yes. In a similar manner, you can find out for Fc and Ft. That I leave it up to you. Try to figure it out, although I'm going to give you the direct relationship. Okay? Yes. So I'm going to give you the direct relationship, and it goes like this. That R is equal to Ft by sine, it is beta minus alpha. It should be beta minus alpha. Yes, sine beta minus alpha. And Fc, if this is sine beta minus alpha, it will be cos beta minus alpha. Very good. So you have found another relationship like this. Very good. So basically, I am referring this one also for simplification. Yes. So you can see all these 6 forces can be related to each other, because this R is the common ratio. R is the resultant. Okay, this R all are same. Yeah. So these two are the measurable forces, and we can measure them using the dynamometers. And these two forces, and these two forces, in totality 4 forces, are non-measurable. Why? Because they occur in a dynamic environment, and they cannot be simply measured. Okay, so that is why we need a method which can connect the measurable to non-measurable forces, so that we can calculate the unmeasurable forces also. Right? I hope that it is pretty much clear to you, and so if it is not clear, simply just rewind the video once again and watch it continuously. I am pretty sure, I am 100% confident that you are going to understand each and everything clearly, right? So my friends, this was the analysis of orthogonal machining, where we covered 3 things, which is firstly the velocities, okay, and the shear angle, and your forces, analysis of forces. And before that, we understood the concept of orthogonal machining and oblique machining operation, and why they are known as 2D machining and 3D machining respectively. Okay, so I hope that it is clear to you, and that's all. We have understood it completely, and now let us try to understand how the problems from analysis of orthogonal machining are asked, and how they are needed to be solved. All right. Alright students, so have a look here, and in this problem you will find a few data are given to you. Actually, usually the problems are asked in the descriptive manner. I have not describing the problem just to save your time, because and I have simply written down all the given data for you. Alright, and what you need to find out is, you have to firstly find out the shear angle. You remember shear angle? It is the angle that shear plane makes with the horizontal. Similarly, you have to find the friction angle, and the shear stress you have to find out. And similarly, power has to be found out, and chip velocity, yes, chip flow velocity, which is indicated by VF. Yeah. So 1, 2, 3, 4, 5 data have to be found out, right? So let us start. So what is the first thing that you are going to do? You have to determine phi. Which formula we use for that? Tan phi equals r cos alpha by 1 minus r sin alpha. So alpha is given to us, which is the back rake angle. It is 10 degrees, but r is not given to us, right? So r is nothing but chip thickness ratio. So we can simply determine from here, r is T1 by T2, and T1 is equal to what? It's 0.127 divided by 0.228. Okay. 0.228. So the value of r that I can have here is, so all right friends, you can see the value of r, it's 0.558. You should also get the same value. And now let us find out the value for tan phi. Tan phi is equal to r cos alpha by 1 minus r sin alpha. So tan phi is equal to 0.558 into cos alpha. Cos alpha means cos 10 degrees, divided by 1 minus 0.558 sin 10. Okay, so when you will solve for this, you should get the value for phi as, let us try to solve it. I am getting 31.27 degrees as the value for phi. Right. So 31.27 is phi. Now let us find out beta. Now how you can find beta? Beta can be found out by using the different relationships that we have got from merchant circle diagram, right? Okay. So what I remember is from merchant circle diagram that Ft by Fc is equal to tan beta minus alpha. If you also remember, if you just open your notebooks and try to find out this relationship, you are going to get, okay, so let us put down the values. 227 divided by 567 equals tan beta, and alpha is given to you as 10 degrees. So 227 by 567 and tan inverse of that. Okay, so beta I am getting as 31.81 degrees. I hope you are also getting the same value. 31.81 degrees is the correct value. Right? Good. Now let us move to the next data to be found out. It's tau. Now what is tau? Tau is nothing but the sheared force per unit sheared area. Now what is sheared area? That is what we have to understand first in order to calculate this. Now sheared area is, I want you to consider this figure. So, can you recognize this figure? Yes, absolutely, because it is the same diagram we are watching in, we are looking at it in three-dimensional format. So, this is the shear angle and this is the shear plane, right? And the sheared area is nothing but, it is the area of the shear plane, right? So, if you can see, if I call it A, this is B and this is C and D, like this, then this is the sheared area, right? So sheared area means BC into AB is sheared area. Now what is BC? BC is nothing but the width of cut, if you can observe. So this part here, this line here, this is B, okay? This is the width of cut. This is width of cut. B is equal to BC is width of cut. And it is 6.35. Now what is AB? AB has to be found out because, and now this is T1. So AB is nothing but T1 by sine phi, okay, T1 by sine phi, and therefore sheared area is nothing but, as I told you, AB into BC. So AB is T1 by sine phi, and what is BC? BC is B. So this is the expression for the sheared area, T1 into B by sine phi, right? So let us calculate A is first, the sheared area. T1 is your 0.127 and B is 6.35 mm. 6.35 mm divided by sine phi. So divided by sine phi means 31.27. And when you will calculate this, you should get a value. Let us see. I'm getting 0.9435 as the value. Okay, 0.9435 mm square. So this is what I am getting. Let us check it once again. Yes, there was some mistake because the area was coming too small. I am getting 1.55 now. 1.55 mm square. Okay. Yes. So 1.55 mm square is the value for the sheared area, and now you have to determine tau. So tau is nothing. Okay, for that we have to determine Fs also, right? Okay. Now what is the value for Fs? Fs can be correlated with it. Fs can be related with the cutting force, right? And for that you have one expression, one relationship from merchant circle diagram. You can use that over here, right? Yeah, so Fs can be written as Fc cos phi plus beta minus alpha divided by sine beta minus alpha. Oh, sorry, cos beta minus alpha. This has to be cos beta minus alpha. Now let us put down the values and you will get the value for Fs. So 567 cos phi. What is phi? Phi is 31.27 plus beta is 31.81 minus 10 divided by cos. What is beta? Beta is 31.81 minus 10. Okay. So Fs, value for Fs is, let us see. Alright, so I'm getting Fs value as 366.85 newtons. This is the value for Fs I'm getting. Now what we can do for determination of tau, simply 366.85 divided by 1.55. Okay. So I'm going to get 236.68. So the value for tau I get is 236.68 MPa. So yeah, this is the value for tau. Let me highlight it. So this is the value for tau. I hope that you are following. Yes, so we have got all these three values. Now power, it's now the turn to determine power, and power can be determined as, so power is nothing but, as you already know, it is force into velocity. But which force and which velocity? Because there are several forces and several velocities. It's Fc into Vc, right? So cutting force times the cutting velocity will give you the absolute power. Now Fc is how much? What was the value for Fc? I have cleared the board. Anyways, yeah, so it is 567. It is 567 and Vc has been given to you. I think it's 2 meter per second. That means it is 2000 mm per second. So when you will solve for this, you should get 1134 kilowatt, I guess. 567 into, yes, 1134 kilowatt you are going to get. Right? So this is the value for power. And in this particular problem, the value for Vc was directly given to you, but in some problems it has to be found out. So the related data will be given to you. You have to use those data in order to find Vf or Vc, whatever, right? So 1134 kilowatt. Now let us determine Vf. Yes, now we have to determine Vf. How can we determine Vf? There is a relationship between Vc and Vf. And what is that? Vf is equal to Vc sine phi divided by cos phi minus alpha. Cos phi minus alpha. So when you will put down the values, let us see what you get. It's 2000 times sine phi. Sine phi means 31.27 and divided by cos. What is the value for alpha? It's 10, right? Yes. So I'm getting 1114 mm per second. Yes. So it will be 1.114 meter per second. That would be even more convenient for me to write. Yes. So when you solve for this, you should get this value. Right. So you have seen we have determined all these 5 values: phi, beta, tau, power, and Vf. And in this manner, you have to use several relations and you have to try to connect them in order to determine the unknown data. Right? So I hope you have understood this problem. Let us try one more problem of a similar kind. And yeah, let's move. Alright friends, so this is your second problem, and again I have simply extracted the datas, and directly you can start solving the problem. It is going to save some time. So these are the datas, and what you are supposed to find out. You are supposed to find out all the 6 components of the forces in this particular problem, right? So which is the first force that you can determine? Yes, you are absolutely correct. It should be the shear force or shear force, right? So because the shear stress is given to you directly, we can find out the shear force very easily. So let us determine Fs first. So Fs is nothing but tau into sheared area, right? So tau is 285 already, and sheared area, as you have seen in the previous problem also, it is T1 into B by sine phi. So simply T1 into B by sine phi. Okay, so T1 is 0.35, B is 3 mm divided by sine phi. But phi value we don't know. So let us firstly determine the value for phi. Okay. Again, using the same formula, tan phi equals r cos alpha by 1 minus r sin alpha. Okay. Now what is r? R is T1 by T2, and it has to be always smaller than 1 because T2 is always greater than T1. I'm getting 0.68, 0.68, right? So let us find out the value for phi. Tan phi is equal to 0.68 cos alpha. Alpha is again 10 degrees. 1 minus 0.68 sine 10. So here phi value will be, I'm getting 37.46 value, 37.46 degrees. I'm getting this value as phi, 37.46. Now we can put this value here, right? And what is the value for Fs? Let us see. It is 492. What I get is 492 point. Okay, it's okay. 492 newtons is Fs approximately. Okay, 492 Newton is shear force. Now, once you have found out shear force, you can determine all the other values of other forces also. So phi is given, alpha is given. Let us determine. You will also need beta, which is the friction angle. Where you will need it? Let us have a look. Because you need to connect Fc and Fs, right? So Fc is what? Fc is equal to Fc is equal to Fs cos beta minus alpha. Fs cos beta minus alpha divided by cos phi plus beta minus alpha, right? You are having the same relationship here, right? Very good. Now Fs is 492 Newton and cos beta minus alpha. So we need beta first. So let us determine beta, and we have got mu here, which is 0.65. So you must be knowing this relationship. Tan beta equals to mu. If you don't remember that, I mean, you can just go back and revise the things, and you will get the same value, same answer, which is tan beta equal to mu. So tan beta is equal to 0.65, and therefore beta is equal to how much? It is 33.02 degrees. So this is the value for beta. Now we know all the values, we can put all the values here. Beta is 33.02 minus 10 divided by cos phi is 37.46 plus beta is 33.02 and alpha is 10. So Fc is, I'm getting Fc as 919 Newton. 919 Newton. Okay. I hope you should also get the same value, because I think this value is correct. Okay, according to our calculation. My calculation is right. I am pretty sure about that. So this should be 919. Similarly, we can calculate Ft, and we know our relationship between Ft and Fc, that it is equal to tan beta minus alpha, right? So yes, let us use that. So Ft is equal to, Fc is 919 and multiplied by tan beta minus alpha means 33.02 minus 10. That's all. That's all you have got. the value, how much it is. So it is 390.4, 390.47. This is Ft. Right. So you can see we have already found out three components of forces, or three forces: Fc, Ft, and Fs. The rest of the things are pretty easy. You can find it out. Let us see. We can do one thing, that instead of relating all the forces with each other, we can simply find out the value for the ratio or the resultant R. Right. R is equal to Fc divided by cos beta minus alpha, right? So that will be R. R is equal to Fc divided by cos beta minus alpha, 33.02 minus 10, right? Okay. Now what is Fc? Fc is 919. So directly put down the value here and you will get the values for this. Yeah. R value is 998.5. Okay. Okay. So this is the value for R. Now you can find out the values for friction force F and the normal to the friction force N, because what is F? It is 998.5 times sine beta. So sine 33.02 and it is 544.11 Newton is your friction force. Okay. Similarly, you can find out the other values for N and Fn. Right. So I am leaving it up to you to find out the value for N and Fn. Rest of the values we have already found out. You know it now. How you have to proceed further. I'm sorry. So yeah. So in this manner, this kind of questions have to be solved. And we started with the computation of Fs, then Fc, then Ft, three forces, and the fourth one here, which is the friction force. N and Fn are left, and this is for your own to solve. Okay, you have to solve by your own, and I hope that you will be able to get the correct answer. Right. So my friends, here we finish our second problem from analysis of orthogonal machining. I hope that you have understood the concept and the way you have to proceed, and the approach also you have understood. Right. So that's all for now. Keep practicing. All the best.